Sure.
Thank you.
It is recorded. Excellent. All right. So I'm going to let you lead with what questions that you wanted to raise. So there's something that you weren't sure about, like in particular.
To be honest with you, I wasn't the one that wrote them down, so I can't remember them right now. But if I remember correctly, Keaton or Losa wrote them down when we were studying. So hopefully they'll have
like questions that you guys raised in a study session or something.
Yeah, we've been studying all week together after school. And so we've come up with like a small list. And we all just basically agreed that we didn't understand surface area to volume ratios. So
okay, cool. Let's text them and tell them to come on. Jump on the call so we can get this done. So come on, kids, get this party started. There's Keaton right there. So Keaton, I understand that you guys have a, hold on, he's not connected. Yeah, he's connected. So Keaton, I understand you guys have a running list of questions about surface area to volume ratios.
Wait, I thought it was just one question.
Okay, well then what is the question?
Chastity, her question was, shoot, what was it? I believe it was just
to like go over polarity.
Yeah, but that's a different thing.
Yeah, that's different than surface area to volume ratios.
I don't remember what the question was for surface area to volume ratio. I thought we went over it pretty well.
Okay, well then how about this?
we skipped it.
Yeah, I don't think she had a question for it.
Okay, well, in this case, can you guys give me 3 methods that cells or organisms use to increase the surface area to volume ratios? And then I've got some practice questions that we can look at too. So what would be some methods that, let's keep it to cells. Let's keep, for at the moment. What would be some methods that you could use to increase your surface area to volume ratios? And just kind of brainstorm it, throw them out there. What do you guys think?
Like, you mean for like cells or organisms?
Yeah, no, let's just say cells. Let's keep it to cells.
I believe there are some cells that have like ridges in them to increase their surface area.
Okay, and that one increase the perimeter, so the edge, right? Those edge, that would definitely work. So if you increase your perimeter, and I can draw that maybe. So let me draw. So if I'm a cell, move this thing out of the way. So if I'm a cell and this is my, and that is my, what I look like, right? That's what the perimeter of my plasma membrane looks like. Well, okay, as long as I'm small, that really works. But what if I increase the perimeter by just, and the volume stays the same, but I'm just increasing the perimeter of that cell, like the edge of that cell. So if I increase and have all these ridges, then I'm increasing my surface area. Now, the volume, the shaded area, that might actually be the same, right? This is going to be shaded. I can't really shade very easily with this pen without, my artistic skills are a lot better than what it appears. But let's just pretend for a moment that the volume is actually equal. All this shaded area is equal. It's what it was. The volume here and the volume here are equal, but because I have extra perimeter around the cell, all this extra area, the surface area is not equal. So in this case, surface area is actually going to be greater on this cell right here. This cell surface area is actually greater than this cell, but the volume is the same. So what's the benefit of that situation? Why do I want to do that? What would be one benefit that you could think of?
There's more diffusion going in and diffusion going out, so it can complete processes.
Yeah, there you go.
Faster.
So absolutely, that's going to increase the rate of passive transport, diffusion and osmosis for sure. That's awesome. Now, what's the inverse of that? If I increase the rate of passive transport, what am I decreasing the need for?
Active.
Energy.
Yeah, exactly. Oh, boop, oh, hold on, I gotta get my shell back. Oh, wrong one. Yeah, I'm decreasing the need for active transport. If I decrease the need for active transport, then I'm gonna be able to conserve energy. So I'll be able to conserve energy. What's another method I could use to increase the surface area to volume ratios in a cell, and for cells? It's another method I could do. You don't have to be right. You just got to kind of think about it.
Couldn't you like cut it up into different pieces?
Yeah, I could increase the, reduce the size, and essentially what you were just saying right there, increase the number of cells for growth, not size. Reduce size by increasing a number. And that's essentially what you're saying, right? Our bodies are made of trillions of cells, not millions of cells, not thousands of cells. We're made of trillions of cells. And that is going to allow us to stay small. Like I said, increase the number of pieces. Increasing the number of pieces is going to increase the surface area. The volume stays the same. And that's going to definitely do the same thing here, right? You're going to increase the rate of passive transport. And that's both in and out, right? So you have waste materials that you've got to get out as well. And you got, resources you need to get in. And then, like I said, waste that you need to get out. It also, don't forget about the enzymatic reactions. So remember Tracy? So in Tracy, we were talking about there's transport, and so this handles transport, but there's receptors, but there's E for enzymatic reactions. And let me draw something else. I'm gonna draw, let me see if I can get my annotate button again. Clear everything up. Using another sound. So what organelle kind of looks like this? And you guys stop me whenever you
Golgi apparatus?
It does. It looks like a Golgi apparatus for sure. It looks like a Golgi apparatus. And what other organelle looks really similar to it?
Smooth and rough ER.
Yeah, so let's go rough ER for a moment. So this will be the rough ER. And I'm going to put these little dots all over. What are those little dots?
Ribosomes.
Yeah, ribosomes. And remember, ribosomes are enzymatic. They synthesize proteins. So if they're synthesizing proteins, that's going to be, remember there's Tracy. So we remember the first T was for transport on Tracy. That's transport, it's supposed to be. The last part for Tracy, we had receptors, we had adhesion, we had cells being able to communicate. And that definitely would be enhanced by having more surface area, because then you have more receptors, you have more communication aspects, intracellular joinings. But they also think about enzymatic reactions. And so I'm going to use two examples for that. That's supposed to say enzyme, I'm sorry. But if I'm able to do that, I'll send a little vesicle, and this vesicle goes over here and over here. But the more surface area I have, the more reactions I can have. The more surface area I have over here, think of the Golgi apparatus. This is going to be just the perimeter of a cell, right? I mean, these are organelles. So if I have a catcher's mitt, like if I'm playing baseball, and I have think of the Golgi apparatus as like a catcher's mitt, you're increasing the surface area of your hand if you're playing baseball, and that's when you're able to catch a ball. Well, if I increase the surface area of my organelle, I'm able to catch vesicles. So you could even write about that. So there's definitely some increases or some benefits to having an increased surface to volume ratio, not even just in cells, but just organelles themselves. Like these organelles have an increased surface area. What about this organelle? This is probably one you guys recognize. What am I drawing here? Kind of looks like a prokaryote. Because it is a descendant of a prokaryote. So let's see, Tracy, what do you think this is?
It's either the cytoplasm or the mitochondria.
Cytoplasm is a clear fluid, so I don't think I can't even really draw cytoplasm. Unless you think I'm talking about like this area outside of the mitochondria, if that's what you thought I was pointing to. I'm just talking about this as a mitochondria.
Oh.
All right. So the inner membrane also has the same situation. What's going on in the inner membrane? All these little places in the membrane. And what do you think is happening here? It's happening here. What process occurs right here in the inner membrane? What process occurs there?
The Krebs cycle, right?
Oh,
The Krebs cycle occurs in the stroma. No, not
Oh.
stroma. Excuse me. The matrix. The matrix. Sorry, I was going photosynthesis on this.
Oh, so then it's the electron transport chain?
Yeah. That's the same thing. That's enzymatic reactions, right? There's an enzyme in there too. So this is the ETC. So the more surface area I have, the more enzymatic reactions I can have as well. So if I were going to be, citing the benefits of this as well, and this is essentially what you'll have to do on the exams. Let me get this back to my mouse. Is talk about increase the area for secretions. If you need to have a secretion, if you need to get something out, you can, if I'm a Golgi apparatus and I'm trying to make some secretions for export. I don't want to have to use active transport, and if I don't have to use active transport, then I'm able to use passive, or the more passive transport I can use, the less the need there is for active transport. And if I don't have to use active transport, then I save energy. Saving energy is just like in a business, it's like saving money. Increase for enzymatic reactions. If I have an FRQ, then I have to do, these are the big points that you want to talk about for sure. These are going to score you points on the FRQ for surface area to volume ratios all day long. Because those really are the meat. That's not the dessert for surface area to volume ratios. These are the real main points of them. Let's look at a couple of questions then. How about that?
Mr. Pope, is our final the last thing that we need to think about going into our grade book?
Shoot, yeah, that's the last grade you have. It's tomorrow. You're gonna take it and be done with it. And then you're gonna say, then you can run outside, spike the ball in the yard, and say, "I'm done. I'm done. I'm ready to
And tomorrow, and for tomorrow, is it like a normal class day, or we just go to your class period and take it?
Yep, exactly. You're gonna come in, and it's gonna take you 52 minutes. That's how long you have. I've designed it to, just in case that we were having it when how they shortened our classes to 52 minutes. So I was like, all right, I'm gonna make this test a perfect, for a 52-minute section. And that's literally how much time that you have. And I'm timing you exactly how much time you would have on the IB test. So it's not more, not less. So I have just the number of questions that you would have if you were given 52 minutes on the IB exam. All right, so first things first, what you guys have seen this question before. Which one of these is answering this question correctly? Which graph represents the change in cell surface area to volume with an increasing diameter? Take a look at it and talk to each other. I'm literally not going to say for 2 minutes. I want y'all to talk to each other about it. And why A, B, C, D are right or either correct or incorrect.
Well, we know it's not linear, right? Because it decreases faster over time.
Yeah.
So it can't be A or D.
Okay, doke. So then we're left with C and D.
And the surface area doesn't increase with the diameter.
Okay.
Yeah.
I mean, the surface area and volume both are going to change, but in terms of a cell diameter, but, or do which changes more quickly is the question.
I think the diameter changes more quickly.
Well, if you increase diameter, I guess is what I should say, which is the surface area, but even though it doesn't have on here, hold on a second, I'm getting a phone call. Where's the phone in here? Where's the phone in this room? Okay, I'm back. I'm sorry about that. Where were we here? We're talking about diameter and surface area to volume ratios.
Yeah, we were.
Okay. And it doesn't have,
Let's see.
yeah, and so we don't have surface area down here. We just have a diameter, right? So, but if I increase my diameter, and assuming it's a circle, just as a circular object would be, so as my cell increases, is volume going to increase quickly, or is it going to be the inverse of that? With a greater diameter, what is going to happen to my volume?
It's going to decrease.
It's going to decrease. It's going to decrease, and absolutely, it's going to. And so, if I increase my diameter, so in this case, if I have a small cell, a very small cell, you know what? Hold on a second. Increase in diameter is going to it's going to decrease. If I increase my diameter, but if they're increasing my, you know, what's really weird about this question? It really doesn't tell us about the shape of the cell. Which graph represents? I think it's C. If they're not really telling us what the diameter looks like, they're telling us. C actually makes sense to me. What do you guys think?
I thought it was C because as it got bigger, the other thing got bigger, but I don't really know.
No, I would, but the shape of this curve doesn't really agree with me in terms of this. It's just showing like an exponential curve. This is exponentially decreasing, but it's still kind of. This is almost like a J curve. This is.
Wait, I thought whenever you increase the diameter, the surface area would always decrease, or it would always increase slower than the volume.
Exactly. It would increase slower than the volume, but we don't have, they're not putting surface area on here. And so if I increase the diameter, this is going, let's split hairs. What are you thinking, Keaton? I don't want to look at the key. I haven't seen the key for this yet.
Well, I mean, I remember in class, like just in general, it was taught that as the cell got larger, the surface area to volume ratio would decrease. Like I'm just going off of
yeah, it would decrease. I agree. It would decrease. But I wasn't looking at this. I was literally looking at surface. I was looking at volume. I wasn't even looking where it says surface area. I'm a complete idiot. I was literally looking at just volume and not seeing the surface area. I'm a moron. Yeah, so that actually it has to be B. Yeah, it's because your surface area to volume ratio is going to decrease. Oh my God, what is wrong with me? How did I not see that surface area? Somebody needs to examine my brain and say, well, why did you not see that? So yeah, that to me, it's got to be B. Yeah, it's B. Yeah, the bigger you get, I was looking at I didn't see this as a ratio. I was just looking at volume right there. That sucks. I think I would typically, if I were writing on an axis, I would have it vertical and not horizontal. And so I really was ignoring this. Oh, geez, that's so embarrassing. Yeah, that would definitely be it. As you get larger, your surface area to volume ratio is going to decrease efficiency. Man, something's wrong with me. Okay, let's try another one. Okay, the image is a cross section of an amphiphily. It grows in coastal sand dunes. Okay, what do y'all know about sand dunes? What do you think the environment's going to be like in sand dunes?
Very dry.
Yeah, it's going to be very dry. Somebody else said something. What was the other term that you, or answer somebody
Dry and arid.
Yeah, arid, right? It's going to be dry. It's going to be arid. It's probably going to be very sunny. So you got very little water and very hot. So do you want to increase your surface area or decrease your surface area? figure out an animal.
You want to decrease.
And for an animal, you want to decrease your surface area to conserve water, but you also have the situation to where you want to increase your surface area to be able to dissipate heat. So you've got a problem, right? So you got some real problems. You want to get rid of heat and you want to conserve water. So you've got some issues here. This is a plant, not necessarily an animal. Looks like it's got a lot of surface area to me. So let's take a look at it. It's got a very, it's round. And then when you get in here, you've got a lot of ridges. So it looks like it's got a lot of surface area, but it's doing something to conserve water. What is it doing? What is this? This is a cross section. So if you saw this and it wasn't a cross section, what do you think the leaf would look like? If I had to draw
What does
this.
a cross section mean?
Oh, a cross section?
Like
What is a cross section? Okay, have you ever eaten a sandwich?
Yeah.
Have you ever eaten a sandwich that's been cut in half?
Mm-hmm.
When you look at a sandwich when it's been cut in half, then you're looking at the cross sections. So let me look. A cross section. This is a cross section. This is a nice way to look at it. That's a cross section. I'm cutting it in half. Here's a picture of the earth. I'm taking a cross section, a slice of the earth. Here's a cross section of the earth. Cross section of a sandwich. That's a cross section of a sandwich. That way you can see in it, right? You can see there's a cross section of a hamburger. And you are able to see what I'm showing you, right?
Yeah.
Okay, good. All right, so if I go back to this, this is a cross section of the leaf. So if I were going to be, let me see if I can't do a decent drawing of this. So it's probably going to look kind of like a needle, probably, and they're cutting it. And then I'm looking at it sideways. It's probably kind of a conical needle-shaped leaf. And we're looking at the cross section of it here. There's the cross section, but it's going to be round. And what is on the bottom of leaves? Remember, we're studying photosynthesis, and I said there's something, air has to get in and air has to get out.
Stomata?
Yeah, exactly, the stomata. And every one of these little do what?
Nothing.
So every one of these little places is where the stomata are. And what goes in and out of the stomata? A couple of things do.
Nutrients and waste.
Well, what goes, okay, what do
And
we
water.
need?
CO2
Yeah,
and oxygen.
Yeah, CO2 goes in. So let's put, this is going to be CO2 going in. And we know what's coming out is going to be oxygen. But it's a trade-off. It's not good. You want, there's something else that comes out, and somebody else said it. What was the other thing that comes out?
Water.
Water, and you don't want to lose the water. You don't want to lose the water. So the strategy that this plant has decided to use was just roll up its leaf. It's just rolled. And so the wind is going to just, this will be wind coming by, and the wind isn't going to get in here and dry it out. I mean, it still has a situation for it's able to get, it has an increased surface area to volume ratio, so it can get rid of heat because it's going to wilt. But at the same time, it's protecting, it's going to protect all of those stomata from the wind. So the wind doesn't dry it out. Because if you guys ever gone outside when it's windy, what do your lips get like? What happens to your lips when it's windy?
They become dry.
Yeah, they're going to dry. It's just going to be osmosis. So you get osmosis, you lose all the wind. It's almost like increasing the surface area of the atmosphere because it's just the winds keeps coming by. If it's still outside, it doesn't happen, but at least as quickly. So their strategy is just to roll it up. So let's see what the question was they want to ask us for this particular one. Oh, here's Randy Rosenbaum. So answer the choice. Answer it. What do you think? Oh, you might not know what this term is. What is the term here? This term. You might want to look this term up. I haven't taught this until we get to ecology, but that's something that's kind of important. A xerophyte. What is a xerophyte? Even if we
A
didn't have
plant that needs little water. That's what it
yeah, at
says.
least exactly. It's like a cactus. So, which would be the correct choice for this question? You guys talk it out.
Well, I don't think it's D because it would want to transpire less easily so it doesn't lose water, right?
Right, exactly. Get rid of that one. That doesn't make any sense. You don't want to transpire because transpiring means that you're losing water. We don't want to do that more easily. We want to do that less easily. So that gives us three choices left. Oh my God, I actually gave you the answer to this.
Yeah.
I didn't realize that.
Because you talked about the wind.
Talked about the wind. Yeah. All right. Well, I guess I did a good job there. Yeah. And that's essentially what they do. They protect their leaves. That's what pine trees do. That's why pine trees have those needles. They underneath of it, they protect and they keep their surface area to volume ratio really high to dissipate heat, but at the same time protect their lower epidermis from the wind. That's what they're doing. Dang, didn't know I was going to answer it for you. That sucks. Oh well, what can I do? Can't be perfect, right? Let's try another one. One of us. I hope they have another good one. Okay, so do you guys probably don't know what a lot of these are. I use these at the very beginning of the lesson for surface area to volume ratios. Can you guys do me a favor and
Wait.
just Google these three terms? Wait, what?
Alveoli, is that the shoot, that was one of our vocabulary terms, wasn't it?
Yeah, it's one of the things I
yes.
said.
They're in the lungs, right?
They're in the
It's
lungs.
a tiny sacs, right? That let
Yep,
blood and oxygen move between the lungs.
Right, absolutely. That's what it is. It allows for gas exchange in the lungs. These are the little alveoli. This is what is getting screwed when people get COVID. The alveoli get inflamed and they cannot have gas exchange and people suffocate. So that's why COVID is so deadly. It's because it infects these alveoli. And then you get this huge inflammatory response and they can no longer have gas exchange. Okay, so take a look at these three terms: villi, alveoli, and nephrons, and then think about what makes sense. Do they have a high surface area to volume ratio or low? And I'm going to draw them. While you're looking those terms up, I'm going to draw some. You tell me which one is which. Okay, so which one is a villi? V-I-L-L-I. Which one? This one, this one, or this one? Let's say 1,
I got it.
2,
3.
3.
One.
The villi. Yeah, this is going to be it. The villi is going to be number 1. So villi or villi are going to be these little ridges inside your stomach. Is there anybody? Who all do we have here? Randy, do you have you ever had the traditional dish of menudo? Does any of your family make that? Do you eat it? You haven't? Oh man. Well, if you ever look inside, you'll see the menudo has its pig intestine that's in there, and it has. Well, there's little. Well, you can see the villi on the pig intestine in the soup. What about? Let me see. What is the name? There's a traditional African American dish in the South. I can't remember. I think it's called chitlins. Has anybody here ever had chitlins?
Yes.
You have had chitlins. Have you, okay, have you noticed the pig intestine in there has all those little ridges on it?
Yeah.
Yeah, that's what that villi is. It's little stringy looking things on the intestine. Okay, so anyway, so that's what this is. So, and then this is going to be which one? An alveoli or nephron? This number 2 that I drew.
That's a nephron, right?
Yeah, it is a
That's
nephron.
That's in the kidneys, right?
Yeah, it's in the
That was
kidneys.
also a vocabulary word.
Yep, it's in the kidneys, and this is a pretty decent kind of drawing of one. To be honest with you, it's pretty apropos for what they look like. And so this would be also the alveoli. So let's see. Do these things secrete? Do they absorb? Do they excrete? What is going on here? So we need to think about this. What is the role of your intestines? Do they absorb, or do they are they going to excrete? Remember, excrete is to get out. This is
They're gonna excrete, right?
They're gonna excrete, like excretions is gonna be like pooping and peeing.
No, that's incorrect.
Okay, so you're going to absorb, right? That's what you would hope that you're doing whenever you eat. You want to absorb your nutrients. So that's going to rule that one out. Now, excretion does work for this one. It totally makes sense. And you kind of excrete here too because you're getting rid of CO2, but it doesn't universally take care of all three. So they're trying to trick you with this one. So I would stay away from that one. They secrete hormones. No, they don't secrete hormones. This one does have secretions. You're going to have to secrete digestive fluids, but this one's going to have to secrete what we call suffocant. You don't know that term yet, but they secrete suffocants, and suffocants are going to be, or surfactants, excuse me, surfactants, and surfactants are going to allow, gas exchange, but they're not hormones, so they're not hormone related. So we're going to get rid of that one. So they're all internal organs. Ooh, they're really screwing you on this one too. Oh man, hold on a second. Do you guys know that? Are you guys? Is our body a cave or a canal? Let me ask you that question. I'm going to teach you something.
Cave or a what?
Are we a system of caves or canals?
With people?
Yep.
I'm assuming canals because they're connected.
Okay, hold on. That's something I haven't taught you yet. Let me see if I can find something. I'll share it with you.
Wait, but aren't these not organs anyway?
Yeah, they are, but they're different. They're trying to trick you. They're trying to trick you. I'm gonna give you a little extra information here. You're like, what?
Is it possible for them to be both, or is that not a thing?
Yeah, they are. It's definitely both, sweetheart. You're 100% correct. Hold on a second. Let me see if I can show you.
Because food goes in and out, but there's also like fat and things that stay in your body.
See. Let me see. Where would that PowerPoint be? Let's see. So I can see what they're trying to do. They're trying to trick you on this particular question. I wouldn't use this question on the test anyway, because we haven't learned enough yet to be able to use a question like this. Here we go. All right, so. This is essentially what I wanted to show you. So this is a cartoon version of our body. So we are a system of caves and canals. Let me get this out of the way. So here you can see this is your mouth, this is your anus, this is the canal part of your body. You can see the villi in there. See the villi? See all these little villi? Awesome. And here is my alveoli. These are those alveoli. These are my lungs because this is for gas exchange. So technically, these are not internal organs. These are not internal. Even though you think about your lungs as being an internal organ, technically it isn't. It's going to be because I can come in here and I can actually get into your lungs without ever having to cut anything. Like I could literally take a clothes hanger if it was malleable, or a string or something, and just have you breathe hard. You could inhale that string down into the bottom of your lung. Or if I could take some sort of stick that was malleable and just push it into your lungs, or if you ate a string and it was like a 40-foot string, you could have one part of the strings hanging out of your mouth and another part of the string hanging out of your butt. And I wouldn't ever have to really damage an organ to do it. I would just let it run through you. So these are not technically internal organs.
That's
how
weird to think about.
Yeah, it is kind of weird to think about. And they were trying to screw you on this question. And they're not really trying to screw you. It's not really a screw you question. It's just a question where they're trying to see how well you understand things. So I'm coming back. You guys can't see the question again? Or not? You can't, can you? Okay, let's get back to it. So we know what villi, alveoli, and nephrons are. The only one that's internal is your nephron. They are not, and all three of them are not internal. This one's an internal. This is technically an external organ, so is your villi. It's still to consider the surface of your body. So in this case, we got to rule out A. The only choice that makes any sense is for molecular exchange. They have a large surface area for molecular exchange. Meaning molecules can pass in and out of these the cells that make them up, or these organs themselves. They have a tiny surface area. All right, so what are some other questions about surface area that you guys have? And I'm going to project this again for Randy, because she might want to write this down, because this is gravy for FRQs, these points. What are the methods that I can use to increase my surface area to volume ratios? What are the benefits of them? You start writing about these, you start scoring points.
I still see the question bank on the screen right now.
Oh, shoot. It hates going between programs. There we go. That's what you missed earlier, Randy. That's good. That's money in the bank. Okay, what other questions do you guys have? I'm ready. Hit me with them.
This is gonna be like really lame to ask, but on the test, what like topics are you specifically expecting us to know?
Basically everything we did, and I'm not kidding. Like if it were me, I would go through. I'll stop sharing. I got a nice cross section using that word again. Yay! Oh God, shut up. Can you see Schoology? Yes, no, maybe so.
No.
I don't see a shared screen right now.
All right, hold on. There we go. You see it. So for me, I would come through here. I opened up your these topics. So we started with biomolecule exams, right? But these were biomolecule. This is where my biomolecules started. This is the vocabulary test, and we started with biomolecules here. I have several questions for biomolecules, but if it were me, what I would do is I would look at my quizzes and see which ones I missed, where I didn't do all that well. And for that, I would review those lessons. At least that's what I hope that you guys have been doing. But I have everything, literally everything. I know I've got questions about biomolecules, enzymes. I opened up these tests. I would go back and look at these tests. Because they're open, you can go back and see what questions you got right, which questions you didn't get right. I would do that. And I would study the ones that I did not do well on. And I would also do the same thing here. So I've got cell theory. Trying to think what else I've got for the, it's not just cell theory, but what are the characteristics of life? Remember that, Mr. Shing. There's active and passive transport. There is one FRQ. It's only for 2 points. Make sure you write about 2 points about surface area to volume ratios. There is osmosis lab. There is enzymatic. There is Tracy. There's endomembrane. Baby, everything that's on here. There's a point. I promise you. If I taught it, there is at least a question about it.
I guess that's good because we went through basically every lesson in PowerPoint up to this point.
Well, if you did, then you're probably going to kill it. If you did that, you're probably going to kill it. And this is the shortest midterm I've ever given in my life. Usually I make them an hour and a half long to take up the entire class period, so you get more practice. So in this case, I have only 52 minutes that this is going to run. I'll tell you, you can't see it yet. I don't think you can see the test yet. Let's see. Yeah, it's right there. I can. Let's see. Ta-da. Whoa! Hold on a second. Yeah, at least Randy laughed. Let's see.
Someone remember it.
Hold on. Let's see how many questions are. Yeah, Randy's like, oh my God. Okay.
You're going to have to edit that out of the recording.
I have to edit out the recording. I love it. Oh, that's so funny. Oh my God, that makes me laugh so hard. I'm trying to, I know there's 35 points. I'll say that. I know there's 35 points. I can't remember exactly how many questions. I just know there's 35 marks. One thing I'll really emphasize to you guys is you need to look and see how many words, what's the word limit? You should always be approaching the word limit. You know what I mean? Whenever I don't know if you guys can see that on your end, but you should see where there's a word limit on open response.
Yeah, it's in the lower right corner usually.
Okay, so yeah, I can't see what it looks like for you guys, but I always type in the word limit. You should be approaching the word limit. I mean, I even think about it myself, like how many sentences would it take me and how many words per sentence would it take me to answer this question to get all these marks? And so then I'll even sit down and just kind of give it a rough estimate and write it out myself and go, okay, how many words is that? And then I'll always increase it by 25%, just in case somebody's a little more verbose. So that's how I'm setting your word limits for you guys. I would also study for you guys where most people are missing points is from here in SLA. And if you're in my advisory, you know this, is the power terms, man. People are not following what they're supposed to do for scoring the marks. I have not been able to give you guys drawings, labelings, measurements, annotations, because you just can't do it on Schoology, excuse me. We're gonna have to really practice this next year. Let me see, there's another one on here. I can't, yeah, sketching. You can't sketch. But they have those on papers 2 and 3 a lot. So maybe not a lot, but they have it, it's significant. I mean, there's enough that it matters. So you should be looking at the others. Some of these are going to be pretty straightforward, like state, give a specific name. So if it's a state, that's probably going to, if it's one mark and it's one state, you can probably do that in about 15 words, if not one word, because state a specific name. You could technically probably do it in 1, maybe 2 words. Listing brief answers, no explanation. That's easy. That's what a lot of people do. They list when they should describe. And describe, when the verb says describe, it says give a detailed account. And people are giving me these lists. And I'm like, what in the heck are you doing? Why would you give me a list when they ask you to describe? If it asks you distinguished, what's the difference? And 2 or more, right? I mean, there's just, so really pay attention to that, because that's where people are not scoring points. And if I've opened up these tests, so you can go back and you can look, and I would look at it and say, well, how often did I identify when I was supposed to describe or supposed to, compare? And did I really compare? So you need to pay attention. I would go and look at these command terms too. Because I know that a lot of people miss points because I think they know what they're talking about, but they don't actually follow the command term. All right. Any other questions from you guys?
Yeah, can you explain the thing about
The thing?
Light pigments and chloroplasts?
Yeah, sure. Okay. Holding on tight to you, kiddo. Give me a sec.
And then
Like, you're
just
talking
like
about chlorophyll A, B, and xanthophylls and things like that.
yeah,
All right. Well,
and then just like a great thing for my endomembrane system, it says it's blank, but it's not. Could I just email it to you instead? I
I don't
sent
even
a
know.
screenshot like a while ago, but huh?
Yeah, hold. You just stay back and let's answer. I'll answer your question individually in a second. You can't see
Okay.
this. So. Yeah, because I think you're saying it's something a little more personal directly to you, right?
Oh yeah.
All right. To you and you alone. Man, I got too many PowerPoints open. Why can't I see this? I gotta close some PowerPoints first. Hold on a second. Not letting me open it. So I'll close some files. There we go. Okay, so you do understand that there is a spectrum of light and there's a rainbow, right? You understand the rainbow?
Yes.
That there is yeah. So if I take white light and I shine it through a prism, it's going to break that light into different different wavelengths, and these different wavelengths have different spectrums. So in this case, like a 380 to 750, the left to the right, some violet to red. So it should and I'm colorblind, so I really can't see any difference between this bandwidth here or these this just seems like dark to light, but it should be violet, blue, green, yellow, orangish, and then red. That's your primary colors, and then they're blending these primary colors whenever they start to switch from one wavelength to another. Shorter wavelengths are going to have blue, longer wavelengths are going to have red. These are lower energy, higher energy. That's how light, actually physically, the light is coming into our atmosphere from the sun. Now, what we have is we have different pigments here to absorb these different spectrums. So like one pigment isn't going to absorb blue and yellow, and another one isn't going to absorb, say, yellow and then blue. They're going to be very specific. Some are they're going to also deal with the frequent, or not the wavelengths of light that are most common. And most common wavelengths that we really have, a lot of them, it really is red and blue. So let me get here. So chlorophyll A and B are both going to absorb blue and red quite readily. We have xanthophylls. We have another, I don't think that it's actually, I know it's not actually on your test, but there are other pigments called xanthophylls. And what a xanthophyll would do is absorb all the green light. There's not very many xanthophylls. Xanthophylls. I think that's how you spell it. I'm not really sure. But nevertheless, different pigments are going to absorb different wavelengths of light. The point that you really want to remember, though, is chlorophyll A and B are going to get your reds and your greens. They're going to get both. Your carotenoids are also going to be in a little bit same range, but your xanthophylls are going to get these other pigments in here. We're mostly reflecting the other light, though. So the reason that plants are green is because plants, if I'm not, this is absorbance. You have to look at this axis here. This is absorbing. So these are absorbing these pigments, and that means if they're absorbing, that what would be the opposite of absorbing? If I want
reflecting.
to reflecting. So this is what reflectance would look like. And so what you're getting here is this reflection of light. So this is all reflection. I could put it over here. This is reflection. So plants look green because they're reflecting green. This is my terrible writing with a mouse. So they're reflecting here and they're absorbing here. And what that really looks like, technically, clear this. Notations. Clear drawings. Clear. It's not letting me clear it, is it? Yeah. Is this. So it's chlorophyll. It's a chlorophyll molecule. A chlorophyll molecule is in the thylakoid membrane, and it's catching that light is hitting it. It's absorbing that light. And what it is a piece of magnesium. Let me see if I can have magnesium. There it is. Right here. This is the chlorophyll molecule. It hits it. There's magnesium in here that's holding an electron. And it lets go of that electron, and then it goes into electron transport chain. That's really all that's going on. Is this pigment is going to, in this case, let's say this is blue light, and it excites this. And then there's all these electrons that are getting excited. It hits magnesium. Magnesium's already holding an electron. There's an electron that's pushed into it, and it kicks it free. You don't really need to know all that, but that's exactly what's happening. Maybe there's a picture of it in here. You don't need to know as much as it's giving you. Let me see if I can find a picture of it. I think there might be one in here. And does not appear. Yeah, it does. There it is right there. Ta-da. That's that magnesium right there. That's a central, that little bitty piece of magnesium that's holding that electron, kicks it off. Okay, so that was another question. What else do you guys have?
I wanted to ask a question about how polarity works, because oxygen is a polar molecule, right? Or I mean, no. Water is a polar molecule.
Water
is what it. Yeah.
Yeah.
So that means it has a positive side and a negative side, correct?
Yes, it means it has a positive and negative side. And it's, in this case, it's extremely equal to one another. I mean, it's like, it's the opposite on either side. There's a +2 and a -2 on, depending on the side. So what's your question there?
So where is the positive side and where is the negative side?
Okay.
I'm assuming the negative side is on the oxygen head, right?
Well, let's just draw it out. So what do you have in the nucleus of an atom? What's in the nucleus of an atom?
Like DNA?
No, nucleus of an atom, not a cell.
Protons and neutrons?
Okay, so what's the atomic number? Let's see, atomic number of oxygen. What is the atomic number of oxygen? Somebody
It's
help me
8,
out.
I believe, right?
It is, it's 8. So it's going to be, we got 8 protons and we've got 8 neutrons.
Oh, wait, I just realized we can't see what you're drawing right now. We're still looking at PowerPoint.
Shoot. Okay, here we go. So I have 8 protons and 8 neutrons. So is a proton positive or negative?
Proton is positive.
It is. So it's positive. Now this is going to be the center of the atom. I'm not going to draw these little dots. So if I have 8 protons and I'm not an isotope, how many electrons do I have?
8.
All right, 1, 2, draw the shell around it. Nice. And 1, 2, 6. All right. Nice. So this is, I'm going to leave a little gap here. They could take another one. They don't. Remember, you can have 8 electrons on the second shell of an atom. But you've got a point here and a point here where they're missing. But we still have 8. So let's count. I've got 1. These are going to be negative. Put little negative signs. 1, 2, 3, 4, 5, 6, 7, 8. So this is oxygen. Nice. Now I'm going to draw hydrogen. Hydrogen only doesn't have any neutrons. It just has 1 proton. So it's got 1 proton. It's a positive charge. Put one over here. 1 proton. It's a positive charge. Excellent. So I've got positive, but they also have 1 electron. But they're going to be covalently bonded. So let's see. It's going to covalently bonded. And now I got a negative here and a negative here. Now, electrons, they want to go, remember, opposites attract. So in this case, like a LOSA Are you a good girl or a bad girl? What are you, Alosa? What are you, Alosa? Good or bad?
I'm good.
You're good? All right,
Yeah.
that means you're looking for a bad mate. So let's say Alosa's mate, it's gonna be bad news. So you know when you guys come to your 10-year reunion, Alosa's gonna have some turd in tow because she's such a good kid. She's gonna be looking for a bad mate. That's how it kind of works, right? That's the opposites attract.
Tabitha, what does that say about you and Dev?
What does that say about what? What does it say about what?
and Dev.
Nothing.
All right, she and Dev. So are Dev? Are you and Hairball? Y'all are a pair?
Just say yes, Dev.
I didn't say anything.
Yes.
That's so funny. Oh, y'all are a pair. All right, so Dev, are you good or are you bad?
I don't know.
He's
Both.
Yeah,
he's
think
so
you're
well
No.
Well,
Both?
that's
I
so
don't
smart.
know. No.
You could say that you're both, that you're polar and that she's polar, and that because two polar molecules can get along. That's nice. That's the best answer anybody's ever given. Actually, Hairball, stick with him. That's pretty clever. I like that. Okay. Nevertheless, I've got 10 electrons. And I've got eight on that outer shell and 2 on the inner shell. So I've got 8 electrons, and they all want to hang around the nucleus of oxygen because oxygen's got a positive charge of 8. They don't want to hang around here because there's only a positive charge of 1. 8 is greater than 1, so the electrons want to hang around oxygen. So the electrons aren't going to be orbiting the proton for the hydrogen anymore. They're going to be orbiting more so most of the time the oxygen. Occasionally maybe they'll stray and jump over here, but they're really going to be staying over here. So, but the hydrogen's still chemically bonded, but covalently bonded to this oxygen. So we have 8 over here, so it's a +8 because the oxygen has 8 protons. So I've got +8, but I have -10 for my electrons. So overall, the charge over here is going to be equal to -2. Over here, though, I don't have any electrons hanging around my protons for hydrogen, so I have an overall charge of 1 + 1. And that is going to be +2. So I've got a -2 on one side and a +2 on the other. And that is perfectly polar. Absolutely perfectly polar. There are other molecules that are polar too, but they might have, on one side it might be like -3, on the other side it might be +5. So they're not perfectly polar. They're just and this isn't adding these up. I shouldn't have put those together like that, but they're just not perfectly polar like water. Water is absolutely perfect. So remember, polar will dissolve polar. So in this case, sugar is polar. So if I wanted to, and that's what this sign should say. I shouldn't put equals. Hold on, let me put this in a different way. There we go. Get that out of the way. So polar will, it's so hard to write with the mouse, will dissolve polar molecules, no problem. So polar. And so in this case, that would be like sugar. So sugar is polar. And you can dissolve sugar in water. You know that water is polar. So polar will dissolve polar. But oil and lipids are not. Remember, lipids are the opposite of this. So lipids are going to remember just chains of carbon with hydrogen. And the hydrogen, is the hydrogen positive or negative? What do you guys think?
Should be positive because it's not donating, but its electron is hanging out more with the carbon than it is itself.
Right, it's going to be hanging out with carbon because carbon's got an atomic number of 6 and hydrogen has an atomic number of 1. So that electron is going to be hanging around the carbon and not hanging around the hydrogen. So these are just going to be positive all the way around it. It's just completely positive. Sucks. Doesn't work very well. At least not with water. It works great for what it does. It's just not going to dissolve in water. So if I put oil in water, the water is just going to, it's not going to mix at all. It's not going to dissolve. Okay.
So does that mean that water has 3 poles? Because it has like, or is the attraction
What do
between
you
the
mean?
two hydrogen? Like
Oh,
whenever there's like a hydrogen bond, it can form between like both hydrogens, right? On
nope.
different molecules.
I'm going to draw it. So this is water, the Mickey Mouse molecule. So hydrogen bonds are going to be between their attractions. This is the hydrogen side connected to the oxygen side. So this is the oxygen side, this is the hydrogen side. This is how. Boop. And then if I draw another water molecule over here, this is going to be the oxygen side, hydrogen side. That's what it looks like. Sort of. I mean, it doesn't. You don't actually see the hydrogen bonds. I say it looks. This is a model of what hydrogen bonds would look like. It's just this attraction between oxygen and hydrogen. And these, and this is when it's a fluid. Hydrogen bonds straighten out whenever they're frozen. So that's why water expands. And so if I took this line, and let's say this is going to be, I don't know, let's say that is going to be 10. I should say micrometers, 10 micrometers. So if which it's not, but it's smaller than that. But if I were to, that's the distance between here and here. But if I were to stretch this out, it's probably more like 30 micrometers, right? If I stretch that bond out. And so if I have a can of Coke and there's water, it's mostly composed of water, all these little squiggly hydrogen bonds straighten out. And when it does, it takes that Coke can and makes it burst and blows up. It starts, you know, you give the force inside. It's from those straightening hydrogen bonds. Then when it happens is you get an explosion. If this, you guys do see this is supposed to be a can.
It's like exploding or something.
Yeah, it's an exploding can.
Yeah.
Exploding can. Yeah. And it's all because these hydrogen bonds straighten out. But that's just an attraction between the negative and the positive. That's the attraction between what Elosa and her mate, not Dev, and not. Actually, I guess it would be. This would be just like. This would be like a Dev hairball because these are polar. They're both good and bad. Nice. So the analogy for Elosa and her mate's going to be different. This would be her mate, the positive, and Elosa, the negative. Oh no, hold on. You're the positive, right, Elosa? So this is Elosa, and this is her mate. I want to see her face when I say that. Let's see. Where are you? Over here? Elosa? Oh, you have your camera.
Is not.
Oh my gosh! I thought you were going to give me a look of disgust. Y'all out somebody else. So y'all out Deb and Hare. Who else has made a pair in this group?
I think everybody else is single as a Pringle.
Single as a Pringle. That's what Blake said.
Yeah, that's
the
one
other
way to
day.
describe it.
Yeah, that's what Blake said the other day. I asked him. I said, he had this kid. All right, it's a long story. You don't want to hear the story. Single Pringle. But I feel like Pringles are stacked pretty tightly in a tube. I've eaten Pringles before. I know. I feel like a pair. All right, other questions you guys have? Speaking of Blake, Blake's going to be here in 23 minutes.
For winter break?
Is that Blake's coming? I don't know. I doubt it. I'll tell her whenever he gets over here. So what were y'all going to say? Somebody said something.
I was just asking if he was coming for winter break.
Well, he came home like he came home the Friday before Thanksgiving for winter break. They shut down. He took his finals already. He took his finals 2 weeks ago. They shortened their semester so they didn't want the kids coming home bringing COVID back to campus and then going home again 2 weeks later. So they just shortened the semester to 14 weeks. They had 14 weeks to get everything done, and then they went home for Thanksgiving and took their finals on Monday, Tuesday, Wednesday after Thanksgiving. One of his finals was 3 hours long. It's ridiculous long. Awful. Okie doke. What other questions you guys have? What I would do if I were you also, I'd go through these things, but I would not stay up late. I'd want to be fresh, with a fresh brain. You think, get some sleep. You always think better when you have a brain that's had some time to sleep. So don't stay up all night studying. That'd be a bad idea. If y'all don't have any other questions, I'm going to bounce. So it's time to speak now, forever hold your peace.
I don't have any other questions, but my other thing.
Yeah, so you can hang back, everybody else can bounce. All you other ugly kids gotta leave. Y'all leave, I want to listen to y'all. Let it loose, I came back, stay back and answer the question. If it's not too private, you can go ahead and ask it now. So what was it?
Yeah, it was the endomembrane system we did a while back. It was like when power, I think it was like 3 weeks ago. And then I looked at it, and then it was like, it said, or you left a comment that it's blank. And then I sent you a remind. And then I sent you a screenshot of it.
Then let's go look.
Okay. But I think the screenshot was like bad, so I could always email it to you.
Let's just see if I can find it. Your third period, right?
Yeah.
All right. Endomembrane system. Endomembrane. Cells, endomembrane system, elosa. Yep, you got a 50 for it, and you must have not done anything.
But like on my side, it's like completely full, and I sent it to you.
You know what it is? I bet you made a copy of it and then amended the copy and not the original one that I posted. So go ahead and send it to me. Send it to me and remind real quick. Because I bet what you did is you got in there and made a copy of the document, worked on that copy and not the actual document. That's my guess.
Gotcha.
So Dev, who asked who? Did Hairball ask you, or did you ask Dev? How did that work out?
Tab and Dev, I'm sorry I brought it up.
No, it's all
All
right.
right, it's funny. It's funny, Mr. Pope. It's okay.
Yeah, it's fine.
Okay, so I was the one that asked first, I guess, the homecoming, and then randomly we were just like, so we're gonna make it official, or, and then we just. Then
it was random. It was random. You make these decisions
not
randomly,
random. It was like over.
You didn't even ask her why she breathes.
Yeah, you didn't even ask her why she breathes.
Wow, Keaton, I don't like the innuendo you just put out there.
Oh,
Feelings are hurt.
Oh man. Are you going to text that picture to me, Elosa, or have you found anything?
I think I just emailed it to you because texting. Oh wait, no, I got it. I'll just email it to you.
All right, cool. Easy breezy thing to take care of.
It's just B Pope, right?
Yeah, B Pope at Uplift.
Yeah, it was a copy. The title was literally a copy of Elosa.
Yep, that's what it was. That's what it was. I told you. I can't wait for next year when all this copy of this or that is over. I do not like it. And, I took like over the break because I wasn't sure what everybody looked like. And I got his yearbook from 2019, and I looked back at the yearbook to see who everybody was. And I was like, oh, that's who Brandon Osamba is. I got you.
Mr. Pope, you didn't know what I looked like?
Well,
Am I
I
that
knew
easily forgettable?
Well, there's some of you guys, because I know your mom, I know you by default, right? Because I've known you for a long time. But there's a lot of people here I don't know. Your mom has come up here and done so much for the teachers over the years that I got to know who you were when you were a little bitty kid. So that's different. Like Yang, I've known her since she was literally a kindergartner because she grabbed my leg after her first day of kindergarten and wouldn't let go. So I've always known who she was. That's so weird. Hey, I'm waiting on your email, Lotha. Come
I
on.
sent it.
You did not. Amanda.
Yeah, I sent it.
No. Let's see. Maybe it needed to have a stamp on it. It'll show up in a minute. Well, as soon as I get it, I'll look at it, take a look at it, and I'll change it. The rest of you guys, y'all have a question? Y'all need to ask something?
No, I can't think of anything.
Oh, and where are you uploading the recording? Because Chastity wanted to be here, but couldn't.
I'll put it right there under the same folder with the final exam.
Okay.
Sure. I want to see it. I wonder what this will look like. Hold on. Show you how a picture. Let me see. All right. You can see that, right? All right, what's this? I'm going to replay this video. There's a bobcat in this video, and I'll walk right up to it and shot a video of it. Check this out. You see it? Or I don't know.
Oh my
I got
God.
really. Yeah, watch this. Let's do it again. I walk right up to it. Hey, kitty, kitty. Hey, kitty, kitty. It ran. And that was a couple days ago. I was walking, and you know how y'all have cats? Do any of you guys have a cat?
I have a dog.
Well, dogs might do it, but if you have a cat, the cats can take their ears and rotate them kind of like. They kind of do like this. They can rotate in the direction of sound. And I'm walking, and I see an ear pivot my direction. I was like, whoa, what is that? And I'd already seen several coyotes at that point. I thought maybe it was a little puppy coyote hiding in the grass like a little puppy. And like they call them pups, right? So I was like, I want to go look at this little pups hiding in the grass. And so I'm walking over there, and I realized, oh, it's a bobcat. And it never ran. It just let me walk right up to it. And I thought, oh, man, I'm going to get my phone out and take a video of it before it does run eventually. Because I was about 15 feet away from that. Took the video camera, and I pointed at it, and I said, hey, kitty, kitty. And man, it ran off then. It did not like me talking to it. All right, I'm going to let you guys go then. If you don't have anything else, I'm bowing out.
All right. Thanks for the help.
Uh-oh. Hare's getting harassed by somebody. Is that your mom or your dad?
It's my brother.
Oh, your
actually.
brother.
He
Oh,
wanting to buy Pokemon plush toys, and I was like, no, we don't have money.
man. So, Dev, you're gonna have to worry about her brother when he gets a little older. Brothers are always protected.
They're like besties. They're like,
We're almost twins. It's literally a year difference.
and then Paul and Dev, they're like so close. It doesn't even make
Yeah,
sense.
we're all in robotics,
At
so
some
we're all
point,
friends.
Mr. Pope, I'm gonna be completely
Uh-huh.
honest with you. I thought Paul was dating Dev behind my back.
Oh,
She's
I'm,
so weird.
I'm out. Deuces. Y'all be good.